This is the second part of section 1.4. We're going to continue here with example 2. We've now looked at an example where we kind of looked at things by hand and also using technology, using Desmos. The one that we looked at wasn't too bad to work on by hand because it was kind of a nice, simple equation. But the equations can get a lot more complicated, and the technology, or the value of the technology, gets even more so when the equations are more complicated than what we've worked on so far. So let's take a look at that in example 2 here. Our function, I of t, defined this way, represents the sales of Apple iPods in millions, t years after the year 2000. I did want to just make a quick mention of this. This is a really common thing that happens in application problems that involve times like the actual year. Years are really big numbers, and they're not especially easy to work with. So oftentimes we just define a starting year. And once we've defined our starting year, we measure our time from that year. So in this case, the year 2000 itself would be t equals 0. And then 2001 would be t equal 1, and so on and so on. Okay. All right. Discussion, would it be easy to answer questions about this function, like the function values, intercepts, max mins, etc., based only on the formula? Probably not. This is not a particularly nice formula to work with. It's got a square in it, lots of decimals, right? So probably no. And therefore, we're going to use our graphing technology to produce a graph of the function, and then we'll answer all of the questions based only on the graph this time. So I'm going to come over here to Desmos, and I'm going to type in my function I of t. All right, there we go. I've typed it in. Clearly, again, I'm only seeing a little piece of the graph here, so let's use our hold down the shift key and then drag to kind of stretch, there we go, my x and y axis until I kind of have a better, fuller picture of what this graph actually looks like. All right, the first question on our paper said to find I of 4 and explain what it means. So first of all, let me just do I of 4. Again, Desmos totally understands function notation, so I can simply type it in that way. It automatically put the 4 in for the t values for me and gave me a result of 26.66. So I of 4 is 26.66. And keep in mind here, the input was the t value. My output will be my I value. So this is an input of t equal 4. And based on what we were saying up here about our t values, a t of 4 really means I'm in the year 2004. So in 2004, the number of iPods sold was 26.66, and again, that was in millions. All right, next question. Find t so that I of t equals 30 and explain what that means. So this time my t value is unknown, and they're giving me the value of the output. They're giving me the I value. This time, when I come back over to my graph, I want to say, let's see, the vertical axis are the i's. So 30 would be here. It looks like somewhere in the 4th here. And again, somewhere in the, what is that, 10, 11, 12th year, we would hit 30. But if I want any more precise values, remember that I can just add the line, y equals 30. And that will allow me to specifically pick the points that give an output of 30. So I'm getting t equal 4.3 approximately, and t equals about 12.6. So I just jotted those values down. Now, what does this mean in terms of the situation? When we're interpreting years, we have a couple of options. This is still at 2004. It's just a little bit further into the year 2004. And so now we're claiming that 30 million iPods were sold. That's going to happen when you have years. Right up here I had 2004 and I had the 26.66. In a continuous function like this, that's going to happen. As you get further along into the year, your value is going to change a bit. So according to this one, during 2004, 30 million iPods were sold. Here again, this would be during the year 2012, right? 12 years after 2000. Also 30 million sold. Now you might have noticed that I did not round this value up to 13. And the reason is that I said during the year. We haven't yet hit the year 2013. We're still during the year 2012. And typically that's how I'll answer these questions. I'll stay within the year that I'm actually talking about. All right, next question. Find the t-intercepts and explain what they mean in terms of this situation. Let's see, t is my independent variable. So this is where the graph crosses the t-axis, which is going to be my horizontal axis. My independent variable, always the horizontal axis. So I can get rid of that y equal 30. I don't really need it anymore. And let's go ahead and find those t-intercepts here and there. They are 2.05, 0, and 14.86, 0. All right, so what do these mean? Well, it looks like there were 0 iPods sold. This would be during 2002, and that would be during 2014. All right, local maximum or minimum, and explain what that means. Looks like there's a local maximum, the top of a hill right there. And the point is approximately 8.5, 51.7. Rounding there just a little bit. Again, keep in mind, input is t, output is I, right? So we'd be during the year 2008. The sales of iPods would reach a maximum. The most iPods were sold during 2008. And according to our model here, during that year, that number was about 51.7 million. So I'm going to say the most iPods were sold in 2008 at 51.7 million. When you write a sentence to interpret a maximum or a minimum, you want to make sure you don't just say, you know, in 2008 we sold 51.7 million, but indicate why it's special. This is the maximum, so I'm saying it's the most that were sold, right? I'm telling my reader there's something special about that value. All right, next we want to find the I-intercept. That's going to be on the I-axis. I is my output variable, so that's my vertical axis. And again, explain what that means. All right, the I, or vertical axis, I cross right there at 0, negative 38.4. Now I'm going to write down what it means. It's going to sound a little funny, but we're going to write it down anyway. This is our T and our I again. So T equals 0, that's right at the beginning in the year 2000. This indicates a negative number of sales. Now again, that sounds a little weird, and we'll talk about that in just a moment, but what the point technically tells me is negative 38.4 million iPods were sold. Almost every function that we use as a model will eventually, what we call, break down. It'll give us a result that's completely unreasonable, just like it did here. And when that happens, what I'd like you to do is tell me, yeah, I recognize that's model breakdown. The model is no longer working at that point. I'll talk just a little bit more about model breakdown. When an equation or graph, I should probably say, that is meant to represent or model something in real life makes a prediction that does not make sense or significantly disagrees with something that we already know, we call that model breakdown. Let's talk a little bit more about where exactly we would have model breakdown for this particular situation. If I come back to my graph for a moment, I'm actually going to go back and look at the t-intercepts again. Right? Between the t-intercepts, we're predicting a positive number of sales. That's at least somewhat reasonable. But down here, we'd be predicting a negative number of sales. And over here again, we'd be predicting a negative some number of sales. That's definitely model breakdown. So I would say we have model breakdown for t less than 2.05, all these t's over here. And we have model breakdown again when t gets bigger than 14.86, because again, we're seeing negative sales. So I'm going to jot this down and then we'll talk about it. When t is less than 2.05 and when t is greater than 14.86. Those two situations give us model breakdown. Because we get negative sales. Okay. Just a quick caveat, not all negative outputs in every situation are unreasonable. Sometimes they're very reasonable. But in this case, it's the number of units sold. That's not reasonable to get a negative result. All right, if you're told that Apple first manufactured iPods in 2001, does that change your opinion? Well, our model's pretty close, right? We're kind of okay at 2. Maybe we should have had some sales for t equals 1, which is less than 2, but the model's pretty close. In our model, we first started showing positive sales during 2002, right? Once we got bigger than 2.05 all through here, we have small but positive sales. So the model is close. It predicted first sales in 2002. Not terrible, right? All right, if you are told that Apple sold the most iPods in 2008, with 54 million sold, does that change our opinion? Well, remember our maximum up here did indeed occur in 2008. So that part's accurate, although it looks like we underpredicted by just a little bit. So again, we're just talking now about how good of a job our model is doing. Model correctly predicted the max sales in 2008, but a little low. On the actual number of sales. All right, and then our last question, actually I guess it's not our last, we got a little bit more. If we're told that Apple discontinued the iPod in 2020, what do you think about our model now? Now I'm starting to think that we've probably got a problem on the right-hand end of our model. Our model predicted that it would reach 0 in 2014. And so for 2015 to 2020, when Apple was still selling iPods, we were actually having model breakdown. So the model is definitely problematic once we get past 2014. So our model broke down in 2014, and we didn't predict the sales from 2015 to 2020. All right. We're going to add one more thing to our graph. We're going to see how well our model fits with our actual iPod data from Apple. And depending on how old or new your version of the course pack is, you actually might have some typos here. So I'm going to give you the correct number. This version has the typos. Check yours and please correct it with me if indeed you do have typos. I got a little off on my numbering here. 2006 should have actually been 39 million. 2008 should have been 54 million. 2010 was correct at 51. 2012 should have been 35 million. And 2014 was correct at 14 million. That's actually my source for my data. And these are the correct numbers from that source. Had a little bit of a problem when I was typing it up, so my apologies there. Again, correct that if your version of the course pack had the wrong numbers. All right, what we're going to do is we're going to put these actual values on our graph. We're just going to see how well our model, our graph, fits with the actual data. Now keep in mind, t values here for 2004 would be 4, and then 6, 8, 10, 12, and 14. So when I put the data into my Desmos graph, I'll be using not the actual years, but the t values, along with the number of iPods sold. All right, so I'm going to come back to Desmos. And I'm going to have to put some data in, so I'm going to go back to adding a table. But this time, I'm going to go ahead and just let the X1 and the Y1 stay there, because I'm not actually adding data for this function. I'm adding independent data that I know. So my inputs, the t values, 4, 6, 8, 10, 12, and 14. Again, once you've established the pattern, you could just hit enter and it'll continue. And then the number of iPods sold in each of those years. All right, there we go. So what you can see here is our data actually was pretty good, especially over here. On this side, it was a little bit more off, especially at our year 4 here. But it's not terrible. The actual data fits our model fairly well. This is something we're going to be talking a lot more about as the course goes on, how we can get graphs, equations, etc., to fit numerical data as closely as possible. It's often with real-world data not going to be possible to get a perfect fit where the graph is exactly through all the points, but we'll often be able to get close. Kind of like our model here was pretty close to the data, but not quite perfect. All right. The last question here asks, looking at the relationship between the graph of the function I of t and the actual sales data, for what range of years do you think the model best fits the data? So it looks to me like really, well, it's not terrible here in what would that be, at t equals 6. So maybe starting in 2006 until about 2014, we have a pretty good fit. This is a little bit subjective, right? If you said, I don't really think it was a very good fit until here in 2000, what would that be, 2008? I couldn't argue with you. So this is a little bit subjective, but I do think it was not a great prediction for 2004, so I didn't include that one. Oops. So I'm saying about 2006 to 2014, pretty good predictor. All right, we've got one more example here. Our function P of t represents the average price of a new home in the United States in thousands of dollars in the year that's this time t years after 2010. So notice t equals 0 represents 2010. So t equals 1 would be 2011, and so on and so forth, right? All right, the first thing we're supposed to do is just use technology to graph that function. So I'm going to go pop over to Desmos, and I'm going to get rid of all the stuff that I've already got on here, just that little gear again, and I'm going to delete everything and start fresh. And I'm going to type in my P of t function. By the way, to get the square root, down here, if you ask it to show you the keypad, there's a bunch of options down here for when you need them, special symbols. I need that square root right now. So there's my function. All right, you might think, first of all, why didn't it graph it? But if you look at the numbers in my function, they're pretty big. So it's probably simply a matter of nothing shows on my graph because I don't have a very good window. So I'm going to try something here. Since I see nothing, I'm going to come over here and use this zoom out feature. And I'm going to just kind of keep on zooming out until I finally, there we go, I finally see something. Right? Now from there I can adjust a little bit. Maybe I want to drag it over because there's nothing over here. And that gives me a reasonably good picture of my function, although I might have way too big of numbers on my x-axis, or my t-axis really, right? These were years after 2010, and we can't go 1,000 years after, so maybe I'm going to go ahead and get some slightly smaller values here. Just to make them a little more reasonable. All right, that's not bad. So I've got my function, and the first thing that it asks me to do is to find the p-intercept and explain what it means. By the way, I probably should have said this on the last example, and I didn't, but one thing I might encourage you to do, especially if you tend to get confused as to which intercepts you're being asked for, label your axes. If I go into the little graph settings, my x-axis, my independent variable or input, is t. My dependent variable or output goes on the vertical axis, and that's p. That way, from there on, when you're asked questions, you know which axis represents which variable. It just takes a moment, and it can really help as time goes on. All right, so in this case, we want the p-intercept, where we cross the p-axis. right there is 0,264. All right, what does it mean? Well, again, remember, our input variable is t, output this time is p, the price, and t equals 0 represents 2010. So in 2010, average price of a new home was $264,000. And you can either write out the word thousand, or you can just add the thousands. That's up to you. All right, find P of 4 and explain what it means. I could by hand plug the 4 in for T, or I could just say, let's let Desmos do the math for us. If I want P of 4, I get 344.22. So again, what does it mean? Well, we've now gone 4 years past 2010, our starting year. So we're in 2014. And that average new home price has gone up to a little over $344,000. And again, you can either write the word thousand, or if you want to go and move your decimal point over 3 places, you can write it in actual money, $344,220. Or again, if you prefer, you can just leave it like that. Do be sure your reader is seeing that thousand, though, one way or the other. Otherwise, we all want to go back to 2014 and buy a new house for $344.22, right? So you want to avoid the misconception that will happen if you don't somehow show that you're working in thousands of dollars. All right, we're next supposed to find P of 10 and explain what that means. So P of 10 just plugs 10 in for the T value for us. And that's about 390.84, let's call that. So now we've gone 10 years past our starting year. So from 2010, that would bring us to 2020. Our average new home price has reached $390,000, or $390.84 thousand. Or $390,840 if you want to write it that way. Okay. We're now given some actual data. And again, you can see my data sources there if you want to check that out for yourself. For various years, we're being shown the average price of a new home, actual data from the US. And the question was, do you think that we've got a good model? Do you think our graph, our equation and our graph, are good models for this data? So we can do a couple things. First of all, we could check out the values that we already have, right? We had predicted in 2014, our prediction was 344.22. That's pretty close. I think my model's working out reasonably well at that point. And we also predicted 2020. We predicted 390.84. So at least based on those two predictions, I feel like my model's done a pretty good job of predicting the actual average price of a new home. If I wanted to check it out even further, like we did last time, I could put this data into Desmos and see how well it lines up with the graph. So let's practice doing that for a moment. I'm going to put my t-values in here. 2010 was my starting year 0. So this would be 2 years later, 4, 6, 8, and 10 years later. And so I'm going to have Desmos plot those points and see if it comes pretty close to my graph. So I'm going to add a table. And again, these are my own points. They're not P of T points. So I'm going to leave the X1 and the Y1 this time. And I'm just going to type in the points that were in the table that was in your course pack. All right, looking at this, those points look that they are pretty good. I'm going to look at just a little bit, expand my graph just a little bit here. I don't need the very large values of t that I had. There we go. A little off in 2000 or 2012, I guess that would be, but overall, all of those points are quite close to the graph. So I believe in this case, yes, so far, it seems like my model is doing a really good job of predicting the actual values. All right, let's answer a couple more questions about this particular model. In part F, we want to find t so that P of t equals 400. So this time I know the output is supposed to be 400. So I don't need to see these points anymore. I'm just going to turn them off. And I'm going to add the line y equals 400 to my graph. And that way I can quickly locate the point right there that gives me that output or that price of $400,000. And the t value there is about 11.5. So what does this mean? Well, let's see. Again, we started in the year 2010, so this would be during the year 2021. Our price would be reaching the $400,000 mark. All right, actual reality data. The true average price of a new home in 2021 was actually $454,000. For the first time, we're off by quite a bit, right? All of the other data points, our predictions were really close. We saw it on the graph. We saw it with our predictions. We're now off by quite a bit. So yes, we've probably got model breakdown here. Sometimes it's just a matter of the model no longer being valid. And other times, we can actually say, hey, I actually know something about what was going on in the world at that time to explain why the model broke down. What do we know that may have actually caused our model to be so far off in 2021? Well, of course, we all know that following the pandemic, we had lots of supply chain issues, like lumber prices were through the roof back in 2021, right? There were a lot of things that occurred. We had that great big housing bubble where there were not enough homes and being sold and you know, too many buyers, all that kind of thing. So we know that because of supply chain issues, after the pandemic, We know there was a housing bubble. More demand than supply. Right? Those kinds of things caused price to go up. And that's why our model didn't predict as large of a value for the average price as the current, or as the reality was. Just out of curiosity, we can also ask ourselves the question, how long would our model have predicted it would have taken for that average price to have become $450,000 or $454,000? Well, let's see. For the price to be $454,000, P would be 454, right, since price is in thousands. And let's go back to our graph and see if we can figure out what year that happened on the graph. Let's see. I'm going to change this y equals 400 to y equal 454. That's way out here. A t-value of about 22.4. So let's see. Again, our starting year for this data was 2010, so that would have been in 2032. So essentially, the issues with supply chains, housing bubbles, etc., advanced the price about 10 years ahead of its time. All right, that brings us to the end of 1.4. There's a lot of material in this section, and in particular, if you haven't done a lot of using Desmos in the past, really encourage you to play around with it, look over these problems, get yourself to using it when you're doing homework for this section, and get familiar with it. We will make a great deal of use of Desmos in this class, and getting comfortable with it early on is going to be really helpful.